Hello. In this video, we are going to look at limits of multivariable functions. The way in which we're going to look at limits of multivariable functions is in comparison to limits of single variable functions, the limits that we covered in Calc 1. So we're going to start off by recalling from Calc 1 the precise definition of a limit. Okay, so what does the precise definition say? It says that the limit as x approaches a of f of x equals L if for every epsilon greater than 0, there is a corresponding delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So what does this say? How does this work, right? So the way that the precise definition works is there's really two pieces to it. There's kind of two lines here, right? There's this line that says if for every epsilon there's a corresponding delta, and then there's this line about absolute value x minus a and absolute value of f of x minus L. So if you're going to try and understand how this works, you can really break it into two pieces. Okay, we can break it into this piece, which doesn't really fit in the box. There we go. And then we can break it into this second piece. Right. So what do these two pieces say? So this first piece, if you wanted to translate it, it just says that if for every epsilon there's a corresponding delta. What that's saying is it's saying that there is a link between epsilon and delta. And in particular, it's saying that that link if delta decreases, then so does epsilon. So that's the link. So a link exists such that if delta decreases, then so does epsilon. So that's what that piece says. And that's an important piece to going through and using the precise definition to try and prove that a limit exists, is that you have to have a link between epsilon and delta, and that link has to, the way that link has to work is that if delta decreases, then so does epsilon. And I'll explain the way that the links fit together. So if you're familiar with all this and you understand the precise definition, you just want to skip ahead to the multivariable explanation, then by all means. But I want to make sure that everyone watching understands the way that the Calc 1 definition works so that we can then work together to understand the multivariable definition. All right, so a link exists. If delta decreases, then so does epsilon. All right, what does the second piece say? How do you translate this? All right, what it says is that what this is saying is that's the distance between x and a is delta. And what does this piece say? The distance between f of x and L is epsilon. Okay, if you have a link between delta and epsilon such that if delta decreases, then so does epsilon, and if the distance between x and a is delta, and if the distance between f of x and L is epsilon, then when you fit all that together, what you end up with is you end up with the idea behind a limit. You end up with our notion of a limit, right? So let's translate the limit into the language that you use in Calc 1 so that we can more easily kind of tie it all together, right? So what's the language that we use in Calc 1? We say if x approaches a, then f of x approaches L. And so if you have this and you have this, then the combination of those two produces this, right? It produces it precisely rather than imprecisely. Like this definition is imprecise. What do we mean by approach? Whereas this definition that we've got here is precise. It has distance measured in it. It has a bunch of mathematical language. For every, there's a corresponding, all that stuff, all this mathematical structure fits together so that it precisely defines this idea, right? But what we want to be able to do is see that this does produce this idea. And the way that you can do that is with the following logic, right? So let's put it together and then you can see how it fits. And then when we're done, we'll move on to the multivariables. This is just reviewing Calc 1 here. We can put all this together. What does that say together? All right, if the distance between x and a is delta, and delta decreases in size, then what happens? To x and a, right? So think about that. We have, if the distance between x and a is delta, and so just to be clear here, absolute values are a classic way of measuring distance. That's why there's absolute values in the definition. If the distance between x and a is delta and delta decreases, then what happens to x and a? Well, x and a, if the distance between them gets smaller, then they have to get closer together. So x gets closer to a, or we could say x approaches a, right? Think about that, right? So if you've got the distance between x and a is delta, delta gets smaller, x and a get closer together, that means x is approaching a, because a is a fixed value in the problem, right? So if you look at the definition here, a is what's fixed, x is what's changing. So x is approaching a if you go through and have the distance between x and a be delta and you decrease the size of delta. Now, here's where the link comes in. There is a link between delta and epsilon. If delta is decreasing, then so is epsilon. Okay, so since epsilon and delta are linked, epsilon is also decreasing if delta is decreasing. And then since the distance between f of x and L is epsilon, what can we say about f of x and L, right? So if if epsilon is decreasing because delta was decreasing, and epsilon is the distance between f of x and L, what can we say about f of x and L? Since the distance between them is epsilon, they have to be getting closer together, meaning that f of x is approaching L. And that's how the two pieces fit together, right? So you've got these kind of two pieces, or if you want to think of it as three, if you want to separate them out this way, right? So first you've got the distance between x and a is delta, and delta, you go ahead and have delta decrease so that x is approaching a. And then since delta is decreasing and there's a link between epsilon and delta, that means that epsilon has to be decreasing. And since epsilon is decreasing and epsilon is the distance between f of x and L, that means f of x has to approach L. And that's how the precise definition works. It's these two separate pieces. One is saying we have to have a link, and then the other one is saying that we have to have these distances. Okay, so visually, then this is a common picture. I'm sure you've seen this picture before if you've seen if you've seen a lecture on the precise definition of a limit. But they'll go through and they'll draw a picture. And we'll have some function, and we'll pick some spot on here. Let's pick it over here so that it's above this curve. And we'll say this is A, and you go dot, 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 bang, and then dot, 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 and that's L. And then you go through and you draw some parentheses to represent the distance. So, we'd say that the length of this parenthesis here, that's delta, right? So that's the radius about A. And then we say that X has to be inside here. And then you have a corresponding distance over here, epsilon, and we say that f of x has to be inside. And then you can say if you decrease the size of delta, that means this is going to decrease, this radius is going to decrease, which is going to force x to approach A. Then it's going to it's going to shrink its corresponding value epsilon, and that's also going to shrink, forcing the limit onto L. And that's the basic idea, tying the previous information together into a picture. Okay, and so that's a nice recap of the information from Calc 1. So how does that compare with the definition from multivariable calculus? All right, so let's look at multivariable and tie the two together, and you can see the similarities and the differences. All right, so what we'd start off, we would say, well, what we have is we have the limit as xy approaches AB, right? So two inputs, right? So recall from previous video, multivariable functions, you could have two or even three inputs. We're going to focus on just two in this video, but every idea in this video could be extended to three. So we've got two inputs, and so since there's two inputs, they're going to approach two values. And then we have f of xy, and that gives us a single output, so it's going to approach a single value. And so if you were to write it out into the lingo from Calc 1, we'd say as xy approaches AB, f of xy approaches L. Okay, so now the precise definition equivalent looks like the following. It's going to look pretty similar. If for every epsilon, Draw knows epsilon is a challenge today. There we go. Epsilon greater than 0. There's a corresponding delta. Such that if the square root of x minus a squared plus y minus b squared is less than delta, then f of x comma y minus L is less than epsilon. So there's our two definitions. Let's see if I can successfully box them. Did I write straighter this time? A little bit. All right, so there's our two definitions, our two pieces. So this one is the same, right? Means the same as before. So it's just saying that there needs to be a link between epsilon and delta such that if delta shrinks, then so does epsilon. Okay, now what do these say, right? This is the same. I mean, you got f of xy instead of f of x, but this is the same. So what does that say? It says distance between f of xy and L is epsilon. What does this one say? This one is new. All right, so take a look at it for a second. What does that one say? Well, the left-hand side should look familiar, right? We covered this earlier in the semester. What is this? It's the distance between any 2 points, right? So this is also a distance-related definition. It's just instead of a one-dimensional distance, like on a number line, which if you had that, you'd use absolute values to measure. Instead, it's a two-dimensional difference. So this is still the same idea. It's just now saying the distance between xy and AB is delta. Okay, and so from there you could go through and put this together in exactly the same way. Exactly the same way that we did for the Calc 1 definition, right? So you start off, if the distance between xy and AB is delta, and delta decreases, then what happens? It forces xy to approach AB. Okay, and then 2, if delta decreases, then so does epsilon. And then 3, if epsilon decreases, then f of xy approaches L. And that's the basic idea. Okay, so it's kind of a chain reaction. If you've got this fact and you've got this fact, and then you have xy approaching, you have this piece here, that's gonna represent the fact that delta is decreasing. Then once delta is decreasing, then it's just one thing happens after another. All right, so if you had a visual, what does this look like? What's the picture comparison between between Calc 1 and multivariable, between one variable and two variable, one independent variable and two independent variables. So what I'm going to do is I'm going to try and draw what looks like a surface, and I may not be very successful. We'll see. So the idea is we've got some surface. That's not bad. And then below that, we've got some point. We'll say this point, this is AB. Okay. And then if we go from AB, go up till you hit the curve, boom, over. Right, that's our L right there. And then we're saying that XY needs to be within delta distance of AB, right? So when it comes to a number line, you can just kind of put like parentheses to represent distance. What we use when it comes to 2 dimensions is we use a disk. Okay, so I'm gonna draw a solid disk, but it's technically it would be a dashed disk. It just would be too hard to draw. So the idea is that XY, and the radius of that disk, the radius of the disk is delta. And then we're saying that XY is inside that disk, right? Because XY has to be within delta distance of AB. And then for L, you don't change anything. It's still kind of, parentheses, the length of the distance between the center and the parenthesis is still epsilon. And so we still have f of x is inside there. Sorry, f of xy inside there, right? So if xy is inside of delta distance of AB and f of xy is inside of epsilon distance of L, then if you go ahead and shrink this distance, if you go ahead and shrink delta, making this disk smaller and smaller, forcing xy to approach AB, then that will shrink epsilon because there's a link between the two, and that will shrink this interval, right? And so if this shrinks, forcing xy to AB, then this shrinks, forcing f of xy to L. And that's the basic idea behind the multivariable and the difference between the two. The definitions are almost exactly the same. The only difference is that you make one subtle change to adjust for the fact that you have 2 inputs instead of 1, and that change is just the only change is that you have a different distance formula. With single dimension, you use absolute values. With 2 dimensions, you use the distance formula. Okay, so how does this affect calculating limits? That's probably the main thing that you care about. The main reason that you're watching the video is how does this affect calculating limits? The main way that it changes calculating limits is it changes how you actually try and disprove, how you try and prove a limit does not exist. And if we just kind of refresh our memories, right? In Calc 1, how did we show that a limit does not exist? We would show the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of f of x. Okay, so there's only 2 ways to get to a on a number line, either from the left or from the right. And so different limits ends up implying that the limit does not exist, and there's only two ways to get there, left and right. In multivariable in Calc 3, there's a lot more than two ways to get, right? If we kind of look at the picture here, it's maybe a little bit difficult to tell, but if you could imagine this, if we just kind of blew that up, you've got, here's AB, and you've got a big circle around it, right? And then we've got XY is somewhere in here. You know, it could be here. We could just say that's XY. XY is somewhere in here. And how can you get from XY to AB? Well, there's a lot of different ways you could do it. You could go in a straight line. You could go in a curved path. XY could be over here, and you could go this direction. There's a lot of different ways you can get from XY to AB, not just from the left and from the right. And so because of that, it's going to make things a lot more complicated. So that two input is going to be a serious problem. So what do? So we still are going to try and get two different limits. What we do is we show that the limit as XY approaches AB, oops, that's supposed to be a B, of f of XY equals L1 along path C1, and the limit as XY approaches AB for f of XY equals L2 along path C2. So again, to recap, in Calc 1, when you're trying to show that a limit does not exist, the way that you do that is with two different values, and there's only two possibilities, left and right. In Calc 3, if we want to show a limit does not exist, then we still want to get two different values, but because of the nature of two dimensions for approaching AB, there's a lot of different ways to get to AB. And so there's not just one. So because of that, we're going to look to try and find two different paths that we can use to show that we get two different values. So let me show you how that works in practice, right? Let's try a couple examples, and then you can see. And this is going to be the main difference. Outside of this difference, you know, showing that a limit does not exist, the rest of limits is going to be pretty much the same as Calc 1. So we're tackling the hardest, you know, most difficult part of the section first, and then we'll cover the easy stuff at the end. Let's say you had XY, and it's approaching 0, 0. And our function is 4x plus y over x plus y. Okay. And so if we had a visual, so I'm not going to try and graph this function, but just to kind of give us something to wrap our heads around, we can go ahead and draw a hypothetical, kind of like a fake picture. All right, so the idea is here is AB, in this case 0, 0. We've got our surface that's somewhere, you know, we'll just say it's up here above, but it could be below. We've got our surface, and we've got here's the disk that's about 0, 0. And the idea is that we want to go through and show that if we approach along two different directions, we'll get different values. And the directions could be, so you could approach this way or this way or this way. There's a lot of different directions we could approach along, more than two, like there is on a number line. There's an infinite number of different ways. And you notice that all these ways that I approach, I drew, they're all straight lines. You could approach along curves. You could approach, there's lots of different options. There's an infinite number of different options. And so what we're just looking to find two different ones. All it takes is two. So we don't have to find all of them. We just need to find two directions that give us a different result, and that disproves the limit. Even if all the rest all give you the same result, if you've got two that are different, then that disproves it, because for the limit to exist, all of the different directions, no matter how you approach 0, 0, you have to get the same result. Okay. So when we talk about paths, right, this talks about paths. All right, so I'm going to go through and show you what paths to use, because that's going to be a little confusing. All right, so the paths that we're going to use, we're going to start off by approaching 0, 0 along the x-axis. That's a path, right? So if you imagine that you've got the scenario that I've drawn in this picture, right? And you want to go through and calculate a limit along a path. Well, one path could be to go through and approach along the x-axis. So you could head up the x-axis and see what limit you get. And we're going to do it from both sides, like positive and negative. All right, so we're going to approach along the x-axis. So if we're approaching along the x-axis, what do we know about the x-axis? How can we translate that? Well, the x-axis is the same thing as saying that y equals 0, right, in a two-dimensional sense. So yes, this is a three-dimensional problem, but in terms of the stuff we're plugging in things in 2 dimensions. So you can go back to your knowledge from 2 dimensions, right? You could go back to just thinking about it this way, right? We've just got 2 dimensions, and you think about this like you're looking straight down. We want to go ahead and calculate values, and we want to approach 0, 0, and we're going to go ahead and we're going to try approaching along the x-axis. All right, so what do we know about the x-axis? We know it's where y equals 0. So what we can go through and what we can do is we can set y equal to 0. So what this is doing is it's going to restrict this surface. It's going to take the surface by going through and plugging in y equals 0. It's going to take the surface and it's actually going to turn it into just a curve by cutting away everything where y is not equal to 0. Think about it like you're finding a cross section of the surface and you're just chopping through it, right, with y equals 0, with the xz plane. And so what you'd end up with is if we just kind of guess here, right, we'd end up maybe with something that looks about like that. And so we can go through and set y equal to 0. We can chop through our surface. That turns it into a two-dimensional problem. Watch what happens. It's like magic, right? So limit, if y is equal to 0, then y is set. We're not taking the limit of it anymore. So you can just say x is approaching 0. And if y is 0, well, then just plug in 0 for where the y's are. And what happens is you get 4x over x. Just a single dimensional surface, a dimensional limit. And so we can go through a single variable limit, and we can go through and just use our knowledge from Calc 1 to find this limit. The limit as x goes to 0, 4x over x is just 4. Okay, and then we chose a path. We approached 0, 0. We approached our point along that path, and we ended up getting a limit value. So we can try a different path. Let's try a different path. Can we get another result? So we could try, I think logically, the y-axis would be next, right? So to do that, you go through and you can set x equal to 0. And then if you do that, then the limit, we're just going to drop the x from the limit because it's not moving. And so we've got y approaching 0. And since x equals 0, just going to plug in 0 where the x's are. That kills that term and kills that term, and we get just y over y. And the limit of y over y as y goes to 0 is 1. So look at that. We chose a path. We approached the point, for our limit along that path, and we got 4. We chose a different path, and we got 1. See how these are different? Not the same. All right, so for a limit to exist, all of the different directions have to produce the same result. So what we just did is we showed that the limit does not exist. So this limit does not exist. Okay, and so that's the typical way that you go through and do these problems where you're asked to show that the limit does not exist. All right, that's an easy one. So it can be more complicated than just approaching along the x-axis and the y-axis. Sometimes the x-axis and the y-axis get us the same value, and we need to pick another direction. So let's do one like that, because again, this is the meat of the section. These are the hardest problems. The biggest change from Calc 1 to multivariable is disproving limits. From there, the rest of the section on going ahead and actually finding limits where you're not disproving them, it's almost the same as Calc 1. It's very simple. So let's try another one. And let's say we had xy over x squared plus y squared. All right, and so let's say you went ahead and you're like, all right, I got to pick some paths. We're approaching 0, 0 again. So hey, how about we try the x-axis, the good old x-axis. To do that, we set y equal to 0. You just go ahead and do that. You get the limit, x goes to 0. Pop a 0 where all the y's are. You're going to get 0 times x. That's going to be 0 in the numerator. In the denominator, we're going to have x squared plus 0 squared. So we're just going to have x squared in the denominator, right? So if y is 0, you put a 0 here. 0 times x, 0. X squared plus 0 squared, x squared. All right, so the limit as x goes to 0 of 0 over x squared is equal to 0. All right, so you're like, all right, cool. Let's try the y-axis now, and I'll get a different value, and then we'll be done. But watch what happens. Set x equal to 0, you get limit, y goes to 0, and this time it's 0 over y squared, and look at that, it's still 0. So does that mean that does that prove that we were wrong to try and show that the limit does not exist, and that the limit actually exists and is 0? No, we proved nothing. We proved nothing by going through and showing that two different paths get us the same value, right? To go through and prove a limit by using different paths, you would technically have to approach along every path. And so you'd have to spend an eternity choosing different paths to approach along, so in order to try out all the infinite possibilities. And so you can't go through and prove a limit does exist by picking paths. You can only prove that a limit does not exist. Okay, and so since our goal here is to prove that the limit does not exist, we need to pick another path. So what path could we pick? Well, the paths you want to pick are paths that go through 0, 0. All right, so what's another thing that goes through 0 other than the x-axis or the y-axis, right? We could look back at our picture here. So we've got the x-axis. We tried that one. We got 0. We've got the y-axis. We tried that one. We also got 0. What other things go through 0, 0? Well, hopefully you're sitting there, you think about it, and you're like, hey, what about the line y equals x? That goes through 0, 0. I could approach along that line, right? I could approach 0, 0 along that line and see what values the function gives me. See if I get a different value then. And so our next path, we could say we're going to set y equal to x. Oops. I always forget to change back. So we got y equals x. And if you do that, we've got limit, right? So if y is being set equal to x, then that means we're only going to have x's. The y's are going to be gone. We're replacing them with x's. And so we're still going to have a single variable limit. All right, and so if y is replaced with x, we're going to have x times x. So that's going to be x squared in the numerator. And then we're going to have x. We're still going to have x squared there. And since we've replaced y with x, we're going to have another x squared there. And so we've gotten the limit as x goes to 0 of x squared over 2x squared, which equals 1/2. And look at that. Now we've got two different values, not the same. And so the limit does not exist. And that's the basic idea, okay? So when you're going through and trying to show that a limit does not exist, you want to find two paths that get you two different limits. And the paths, sometimes it's as simple as just using the x-axis and the y-axis. Other times you've got to get a little bit more creative and use the line y equals x. And then other times it can become even more complicated and you have to try things other than the x-axis, y-axis, lines. You might have to try curves, okay? That is also a possibility. Now, the next question that you may have is, will I be told to go ahead and prove and show that the limit does not exist? How will I know when to go through and try and show that the limit does not exist? How will I know when to do this? Okay. When should we try and prove that the limit does not exist? Okay, so this is, I'll tell you. All right, so if you have the limit as xy approaches ab of f of xy, and you're asked to go through and find the limit, right, so if we're asked to calculate that, and we try just plugging in AB. So that's, we're going to get to this in a minute. Why would we just try plugging in AB? It's a technique that's used for finding limits in Calc 1 as well. And I'll explain where that comes from in a minute. But so if we try and plug in and we get 0 over 0, all right, so if limit as f of xy, limit as xy goes to AB of f of xy, and okay, hold on, let me explain that a little better here. And we find that f of AB, so you just try plugging AB in, f of AB results in 0 over 0, then you can try and prove that, show that the limit does not exist. All right, so when should we try and do this? Is if we get 0 over 0. Now, did we have 0 over 0 in these previous two cases? So let's say you had this, and you weren't told to show that the limit does not exist, and you went ahead and you just tried taking 0, 0 and plugging it in. What happens? You get 4 times 0 plus 0. Oh, that's 0. 0 plus 0. Oh, that's 0. I did get 0 over 0 there. So that's what would have inspired you to try this method, would be if you just tried taking 0, 0 and plugging it in. How about this one? If we take 0, 0 and pop it in, what happens? You get 0 times 0 over 0 squared plus 0 squared. Oh, yep, 0 over 0 there too. Yes, so that's the typical case, right? So when should we try and show that the limit does not exist? If you're asked to find the limit as xy goes to ab of f of xy, and you find that f of ab equals 0 over 0, then you try and show that the limit does not exist. Why this? What's the origin of this? Where does this come from? So what this is saying is, this is saying that there is a discontinuity. We have a discontinuity at AB. And it's a discontinuity where you could end up still getting a finite value, right? If we had a 0 in the denominator and we did not have a 0 in the numerator, then clearly the limit would not exist. But if we have a 0 in the numerator and a 0 in the denominator, that's the discontinuity case where you could hypothetically have things still end up working out. Okay, so that's really what's happening there, is that it's saying that we're asked to calculate a limit and we have a situation where there's a discontinuity, then we try and show that the limit does not exist. Now, the only issue with the information that I've given you here is that I just tied it into discontinuities for multivariable functions, and we haven't talked about discontinuities. That's a little bit of the awkwardness of this section, is if you go through and talk about showing limits that do not exist, which is the hard thing, the new thing, then it's kind of cart before the horse, because you haven't really talked about the easy thing that would inspire that. And so, so let's do that now. All right. So let's talk about continuity when it pertains to multivariable, and then it will fit much more nicely in with what we just wrote. Actually, let's do this. All right. So in order to talk about continuity, the way that we're going to talk about it is again, we're going to do comparisons. So the definition from Calc 1. We have the limit as x approaches a of f of x equals f of a. What is the definition in multivariable? What's the new one from this class? The limit as xy approaches ab of f of xy equals f of ab. So take a look at those. Right, so what is it? What do we have from Calc 1? It says that if you're finding the limit as x goes to a of f of x, then you can find that limit by just plugging in the input. Right, from Calc 3, how do we go through and determine whether we have continuity or not? If we can go through and just take AB and just pop it right in there, and we end up getting f of AB, then that's our definition from multivariable. Now, here's the thing. Those definitions, they're not worthless, but that's not how you think of continuity. You don't use the definition. At least I'm not aware of anybody who does. Instead, the way that you go through and think of continuity when it comes to Calc 1, and we're going to extend that to multivariable, is you think of continuity in terms of things that cause problems. Okay, so what would break a function? What would prevent a function from behaving nicely, right? And those are the things that are discontinuous. Those are the problems. Those are the discontinuities. And then if you don't have any of those, then you have continuity. All right. So what we do is we actually think about discontinuities, not think about continuity. Well, I mean, you do think about continuity, but you think about it by looking for discontinuities. Right. What causes a problem? I'm going to simplify this. I'm not going to get into jumps and holes and all that other stuff because those are strictly Calc 1 things. Those actually don't really apply to multivariable. You do have things that act like holes. You do have things that act like asymptotic. Like there's still things, but still some similarity. But those terms are terms that are strictly for Calc 1. But we can still extend the ideas, right? And that is what causes an issue in Calc 1 and in multivariable both. And it's a 0 in the denominator. Right. And then 2 piecewise defined functions. So those are our 2 things that cause discontinuities. Now, the 0 in the denominator case in Calc 1, you have 2 possibilities. You either could have a whole or removable discontinuity if you have a 0 in the denominator that can be canceled through manipulation, or you could have an infinite discontinuity. So there's a 0 in the denominator where you can't cancel it. So those ideas, again, are more strictly Calc 1. You could kind of extend them to multivariable. In that if you have a 0 in the denominator that you can't cancel, then there's definitely a discontinuity. Well, there's definitely discontinuity in either case, but you're still going to have an infinite discontinuity, but you're not going to have a whole in the traditional sense if you have 0 over 0 and you can cancel it. So these are slightly different from multivariable to Calc 1, but they still are similar enough, and that is any 0 in the denominator is going to just break stuff, right? There's no way that you can go through and have the function be continuous in the sense that you could draw it without lifting your pen, right? If you want to think of it that way. There's no way that you could go through and draw it if you have a 0 in the denominator. It's still definitely going to break things. That 0 in the denominator, it's not going to be in the domain for the function, so it's definitely going to be a problem. Okay, and so this is the main one that we're going to focus on for multivariable. That's the one really that we're going to look for. Not that you couldn't have piecewise defined functions with multivariable calculus, but they're not as common, whereas the 0 in the denominator case is much more common. You're much more likely to encounter it doing practice problems, and being able to figure out how to handle it is going to be a bigger issue. Okay, so that's basically everything. That's all there is to it when it comes to continuity, right? So when it comes to continuity for multivariable, you have the definitions here, which in a way you could even think of, even though these are definitions, you could think of them as consequences, right? If you don't have discontinuities, then they tell you can go through and calculate limits by just plugging in plugging in a into f of x, that gets you the result, or plugging ab into f of x, that gets you the result. But to figure out whether you can do that, you're going to look for these two cases. Well, specifically this one case, you're going to look for a 0 in the denominator. And if you don't have this 0 in the denominator, what we're going to say is it's continuous. Okay, and that's it. All right, so how does this affect calculating limits? So to find a limit, find a limit where the denominator is not 0, simply plug in the point. Okay, so if you're asked to go through and find the limit as xy approaches 1, 1 of f of xy, not f of xy, sorry, we actually need a real function. The function we're going to use is the one that we used first, 4x plus y over x plus y. All right, so you take a look at this, you got your point, you take the point, and you try and plug it in. If you don't get a 0 in the denominator, you're done. It's continuous there, limit exists, and you just found it. And that is exactly how you go through and calculate limits in Calc 1 as well. That was our final result. So if you recall going through and calculating limits in Calc 1, you might think, wait, it wasn't that simple. We went through and we had to jump through a bunch of hoops. Yeah, well, that was to build up to continuity. Once you had continuity, then suddenly limits became super easy to calculate. You just plug into functions that are continuous, right? And if it's not continuous, then you've got to deal with it. All right, so how about if we had the limit as xy approaches to -3 for the function 3x squared y minus 4, right? No denominator at all. If it doesn't have a denominator, then it's continuous, right? Can't have a problem if you don't have a denominator. So we can just pop everything into that, and let's see, what do we get? So this is going to be 3 times 4, that's 12. 12 times -3, -36, -40, right? Okay. And so when it comes to doing practice problems, you're cruising along, you go through, you plug in 1, 1, it works. You plug in 2, -3, it works. How do you know when to go through and try to disprove the limit? All right, well, just look at how it looks different when you get to the problem we did earlier. You have this one comes up, you look at it and you're like, oh, I get 0 over 0. 0 in the denominator, boom. Well, technically you have 0 in the numerator too. You have to have 0 in the numerator and denominator for this to work. So you've got 0 over 0. That's our try to prove it doesn't exist case. Okay, so hopefully that tied everything together. Okay, with continuity, it is a little bit of an awkward order where you start off by disproving things before you know when you're going to use that technique, and then we talk about continuity, which tells you when you do have to prove it, when you do have to use it. But that's, I think, the easiest way to go through and explain it. All right. Let's just do a quick recap. Going back to the beginning. So we start off, we've got our idea, precise definition from Calc 1, went through and explained it. You can see, visually what it looks like. Then we have similar definition from multivariable. The only difference is that we've changed the distance. Okay. Then you can see the picture. You got the disk instead of the parentheses, that represents the distance around the point. Then the consequence of the fact that you can approach along different directions instead of just the two directions from Calc 1 is that we have to look at paths instead of just, left and right. And then once we've got paths, then you go through and you've got to pick paths and try calculating the limit to see if you get different values, right? And then, we can see that if you go through and you try enough paths, sometimes it can happen. And then the next question is, wait, when should we try and use that? I mean, when does that come up? And then, the situation that occurs when you have 0/0, which is when we have a discontinuity at the point. So that's when you're going to go ahead and try it, is when there's a discontinuity, which gets us to talking about continuity. And so continuity, we've got our Calc 1 and multivariable definitions. When do we have a discontinuity? 0 in the denominator. No 0 in the denominator, you're good to go. And so I went through and showed two quick examples. You could see how easy it is to go through and calculate a limit if we don't have a discontinuity. You just pop it in, and then you can see how, if you're going through and doing practice problems, how it just stops you dead in your tracks if you go and plug in and you get 0/0. Okay, so that covers limits. Oh, there's one other thing I don't want to forget to mention, and that is that it is possible to get 0/0 and still have the limit exist. Okay, so I don't want to give you the impression that it always does exist. There are clever techniques for going through and proving the limit. There's squeeze theorems and other things like that. I'm not going to get into those just because they're very niche cases when it comes to practice problems. Typically, if you're going through and you're working your way through a multivariable calculus textbook, you're very unlikely to encounter those cases, or maybe there's one in out of 40 homework problems. And so it's a niche case. But if you are interested in trying to do it, you can go through and use squeeze methods and other things like that. You can go through and do further research into it. But other than that, that concludes the video. Thank you for watching. See you next time.